what is the determinant of that? When is this matrix invertible? When that determinant is what? Not zero. And this is a fancy little number, but basically this comes from row reducing. This number also comes from, if you row reduce this matrix, it's what it takes for this thing to have two pivot columns, right? And because two pivot columns is what we need for invertibility. Everybody cool on that? Okay, so I'm gonna, this is, you don't need to take notes on this. This is a bunch of crap, but I'm doing a bunch of crap. Why am I doing crap? Because I want to kind of demonstrate to you where the next determinant comes from. So you can kind of just watch me. This is awful, but we'll assume the day is not zero, right? If it is zero, we just do some row operations. And I want to know, what does it take for this animal to be invertible? Well, what it takes is got to have three pivot columns. Everybody agree? And of course, here we'll assume that at least one of these in the column, the top one, is not zero. So if I were to row reduce it, now the way I tell if something's got three pivot columns or not, or how many pivot columns, I row reduce, right? So if I row reduce it, well, what might I do? Well, what I probably should do is multiply the top row. Let me multiply this, both. AU, AB, AW, and AX, AY, AC. That's a row operation that shouldn't change the number of pivot columns as long as A is not zero, and I did assume that. Right. And then what should I do now? Well, I mean, the whole idea, I guess, here is now I can nuke these by using A, right? I can multiply this by U and take this out. I can multiply this by X and take that out. Everybody okay with that? So we'll see what happens. A, B, C. And if I multiply this by negative U and add, that'll take this out. Times negative U and add. Times negative U and add, AW minus C. Right? And now I'm going to do the same thing here, multiply by negative X and add. And then AZ minus CX. Everybody okay? Okay, I've got one pivot column. Everybody agree with that? That's cool. Got one pivot column. How many more do I need for the matrix to be invertible? I need two more pivot columns, right? So would everybody kind of agree that I'm done with this first column? I'm done. It's gone. Think about it. So really, I really need this matrix to have two pivot columns. That's really what I need, right? Everybody agree with that? So if this matrix right here has two pivot columns, it's invertible, right? Now I could do another row reduction, but I'd really rather not, right? Let me ask you this. What does it take for a matrix like this, that's 2 by 2, to have two pivot columns? The determinant to not be zero. Everybody agree with me? So let's just now put this under a microscope, well, or a magnifying glass, and let's look at this thing right here. I want this to be not zero for the whole shebang. So let's see what that little determinant is. This may seem to be painful, but it's better than, believe me, it's better than doing another row reduction. What do we have here? AD minus BU times AZ minus CX minus AW minus CU and AY minus BX. And now I want this thing to be not zero. If A is not zero and this thing is not zero, then what I have is three different columns, right? Okay, let's pray that I do this right. Let's multiply this out. A squared BZ minus AC DX minus ABUZ plus ABUZ plus ABCUX. Right? That's multiplying on this first method. Don't forget my minus here. So this is going to be minus A squared WY. That's going to be ABXW, and it's going to be plus now. Minus AC minus ACUY. Right. And then back to minus BCUX. Okay. What a mess. Anybody see any way to simplify this? Actually, it's kind of interesting because the only terms that don't have an A in them are these two. They can't. Agree? So let's go. Let me pull an A out of this mess. ABZ minus CBZ minus BUZ so you pull an A out of this minus AWY plus BXW plus CUY. Everybody okay with that? Yes.
Should the CBZ be CBX or?
Maybe. Let me see here. Thank you, because that would have been disastrous. Thank you for paying attention. Everybody okay with that? Doesn't seem very useful at this point. However, I'm going to group these A's together. And I'm going to plot negative A for the second one. UZ minus XW plus C on the last one. UY minus DX. Anybody recognize these?
Yeah.
This is, if you look at just this bit here, A times BZ minus WY minus B times UZ minus XW plus C times UY minus BX. This is A BZ minus WY, that's the determinant of that matrix is left over. Minus B. Well, if you take out this here, UZ minus XW. Matrix. UW. XC. And as you might guess, if you take out the first or the last column, determinant of UV. Y, or no, XY. So in other words, it's this times the determinant of what's left over when you nuke the row and column. Minus this, what's left over when you nuke the row and column, plus this times the determinant is left over. And that is the way, how many of you have seen the 3x3 determinant? That's the way that you do this. You'll use it probably from a practical point of view. Well, you use it a lot of places, but in particular, in Calc 3, you probably use it to compute a cross product, something like this. So for example, let's find the determinant of 2, 1, 4, 0, 3, 1, 1 minus 1. And I'm just going to get on my horse and go. So we've seen that for a 3x3, having this determinant be not 0 is exactly what we need for the matrix to be invertible. Let's see what the determinant is here. It's 2 times the determinant of what's left over. So it'd be 3, 1 minus 1, 2 minus 1 times the determinant of what's left over when you do this row in this column. So 0, 1, 1, 2. Slide. Plus 4 times the determinant of what happens when you move the first row in the last column. 0, 3, 1 minus 1. So now it's just a matter of working things out. This is 2. What's this determinant here? Agreed. 6, 27 minus the determinant of this is 0 minus 1. 4. Determinant of this is 0 minus 3. So the determinant of 14 plus 1 minus 12 is 4. This matrix should have 3 pivot columns. Now, let me give you kind of a little theorem here. Well, actually, let me give you really a definition. I mean, let me tell you how to do this. Definition. Let A be the matrix Aij. Okay, so everything here that we're doing depends on it depends on my matrix being squared. Aij, this means I means the coordinate, this is row column coordinate. So A 3, 4 means it lives in the third row and fourth column, right? Okay, then we're going to define the determinant to be this way. Then number one, capital A IJ is matrix obtained by believing ith row and j column. From two, the determinant of A is equal to, okay, so I'm gonna just do that. And then I'm gonna use something in general, is A11 determinant A1 minus A12 determinant A12 minus 1 plus n A1n determinant A. Or if you like the sigma notation, you can write it in this kind of clear form. Some J A1J permanent. So let me give you an example here. We just did one with a 3x3 here. Let me give you an example here. If A is this, then A 2, 3. What do I mean by this notation here? This is the matrix. It should be one size smaller in the following sense. This is 4x4. This thing should drop to 3x3. This is the matrix obtained when you delete the second row, third column. Right? Second row, third column. So this should be the 3x3 matrix. 1, 2, 4, 4, 3, 1, 5, 8, 6. Everybody okay with that? Okay, so this is exactly the formula that we had before. Zeros in this. Let's find the determinant. I hope this illustrates why this is very good. This is important theoretically, and it's important computationally for some small matrices. But this shows you how the problem compounds. So we're actually going to have other methods of computing the determinant along with this one. How would I do this? Well, according to my formula, I just go across the top, alternating signs and take a smaller determinant. But this one is worse than the previous one. This. You nuke the first and the first row of the first column, and I get 0, 0, 5, 3, 0, 0, 0 minus 1. Minus 0. Well, I love zeros, but I really will write this out so that we're all on the same page, even though it's going to be 0. You nuke the first row of the second column for this one, I get 205, 1 minus 1, 0, 0, and 1 minus 1. Okay. Next one, plus 1 comes determinant of. Here's the first row of the third column, I get 205. I get 1, 3, minus 1, 3, 0. And I get 1, 0, 0. Minus 1 times the determinant, finally, 2, 0, 0. Minus 1, 3, 0. And 1, 0. Yeah, okay, so let's actually get a numerical answer for this instead of letting it hang. Now I've got to work these 4 determinants out. Well, actually, I get a little lucky because I only have to work 3 out because this one's dead. Because it's 0 times that. But okay with that? So I've got 3 things to figure out. So determinant of the first one is 0, 0, 5, 3, 0, 0, 0 minus 1. Okay, let's do this. How do we do this determinant? 0 times this determinant, 0 times this determinant, and finally 5 times determinant 3, 0, 0. Yeah. And this is minus 3, so I think. Well, okay with that? Okay, determinant. I'll get some easier ways to do this later, but let's do this. This should be 2 times the determinant of.
I have a class to go.
3, 0, 0, 0. 0 in the middle. Minus 1, 0, 1, 0. That's 0 anyway. Plus 5, determinant of minus 1, 3, 1, 0. This is 0, 0, and minus 15. Everybody agree with that? This is minus 15 also. Okay, so looks like. And finally, the determinant of this mess this is 2 times this determinant, which is minus 3. So this was minus 6. Those zeros were convenient. They helped out with that, right? So let's go back to this. To finish up this example. the determinant of A, assuming I didn't make any simple calculation errors there, is this thing, which turned out to be -15 minus 0 plus 1 times the next determinant, which is -15, minus -6. So it looks like what, -30 plus 6, -24, it looks like. So the matrix is convertible. Makes you sigh, doesn't it? Right? And there were a lot of zeros that helped me out. Let me ask you a question. Here's sort of my argument for we were actually going to do some other stuff. I got through this all right. I'm pretty fast calculator, but I don't think I can do this. So what if you had a 25 by 25 matrix? You have to take the determinant. Suppose you use this technique. How long would it take you? And 25 by 25 matrices, they're actually fairly common, even in things like economics or, you know, things like aerodynamics. They're much bigger. I mean, we're talking thousands of that. Let's just be modest. 25 by 25. Assume that you could do 1 trillion computations a second, like a computer. To do this technique with a computer doing 1 trillion computations per second would take just shy of about 500,000 years to work out a 25 by 25. Now, if you go to a 30 by 30, right, just 5 more, very modest, right? It would take about 8 trillion years, which is about 600 times the age of the universe to do this. So we need other options, right? We're definitely going to need other options. Well, here's a modest option. It really doesn't solve the problem, but for a lot of the small ones that you do, this will be really a nice little trick for small computations that you'll have to do by hand. Let me give you one more definition. Suppose we have a matrix. Okay, so we have this matrix that we start off with. A I is matrix obtained by deleting I12 and J column. So sort of here's your A. I1, I2, I finally all the way down, A1, A2, A J. So Aij, what do you do to get Aij? You delete the ith row and the j column, collapsing down to this is smaller. Right? We define the ij cofactor you take the determinant of that smaller matrix and you vary it by a sign. So if I plus j is even, then it's just the determinant. And if I plus j adds up to odd, then it's -1 times this. So here's the general formula for expansion or getting a determinant expanding by a row or column. So here's the general expansion. Any row or column. Okay, so given the matrix, theorem, which I won't prove, but I will use, theorem, but A told you have a square matrix, and here I guess I want him to be at least 2, probably. Then the determinant of A is equal to AI1 CI1 plus AI2 CI2 plus AIN CI. And this is ith row things. Or determinant of A is A1J C1J plus A2J C2J plus ANJ CNJ. And this is the Jth column. And let me give you kind of a good example of doing that. So really, by the way, first row. Right, so if you take I equals 1, if I equals 1, so you're going first row expansion. If you take I equals 1 here, this should exactly be the formula that I gave you for the determinants there. You may not see the minus sign, but it's contained in here, right? Because the Cij varies in sign, and in the first row, it'll go positive, negative, positive, negative. So here's an example. Let me give you kind of a practical example of where you might want to throw this column expansion at it. So suppose we had to do the following problem. 4, 9, minus 8, 2, 0, 3, 0, 1, 6, 4, 0, 3, 0, 7, 0, 1. All right, I'm going to do this. right, we've had, right, so really, if I go through here. This times a 3x3 determinant, this times a 3x3, this times a 3x3, this times a 3x3. Then I'm gonna go and do 4 3x3s, which involves 3 2x2s, you know. Yeah. That's death on a hot plate. So. Let's not do just variable, but what seems to be the sexiest column on this matrix? Column 3 is good. It is full of zeros, and I'm digging on that for sure. Right. So let's expand by third column. Right. I mean, if I was going to do a row, I would probably do row 2 and 4, wouldn't I? But the third column is even better because it's, you know, there's so much stuff missing, right? So let's do that. Let me go through the formula carefully. I'm going to expand about this. So here I is 3. So I guess I'm going to use that second formula. So I'm expanding column. Determinant of A is Aij, so it's -8 times Cij. So in this case, it'd be 3 1. Right. Plus 0 C first row, it would be 1 3. First row, third column. Right. Second row, third column. Third row, third column. Fourth row, third column. Everybody okay with that? And it's so full of zeros, this is a bloodbath, right? So this is kind of cool. It now comes -8 times the determinant of everything else is dead. This 3x3 matrix I get here. I think this out. So that's 0 3 1. 6 4 3. 0 7 1. Everybody agree with that? Well, this is easy enough. I can just go straight through, but while we're on the subject, let's be efficient, right? So let's do this one. What's the best row or column to expand out on this? First, I'd go first column on this. So let's take a little aside here. By the way, why was this -8? I should really write this out more carefully. Don't forget this. Uh, 0 3 1. Factor C actually has a sign in it, but I got lucky here because what's -1 is 4 power. That's equal, so it's just one, so it stays the same thing. This is -8. Determinant 0 3 1 6 4 3 0 7 1. So let's take it inside here. Side, figure out what this is. Let's find the determinant. 0 3 1 6 4 3 0 7 1. And about expand on the column, right? So this should be 0 times C 1, 1 plus 6 C 2, 1 plus 0 C 3. Everybody okay with this? So of course, these are dead, and that was the whole point. And this is, what do I gotta do here? Don't forget this is -1, 2 plus 1, right? Times determinant of what I get when I this, which is 317. So this is -6, because of course that's the third power. So that's -6 times 3 minus 7 minus 4. Right, okay. So this thing is 24. So the whole thing is -8 and 24, which is -1. If I follow computations, all right? Now, some people ask about, oh, how can we check these problems? There's always ways, and this is what makes you better at math, checking things. You want to check this and you have the patience to work it out, expand your matrix about, do it one way and then expand about something else, right? If you get the same answer, I almost guarantee you did it right. Yes, is there a question? Okay, any questions? Here is another theorem, and this will be the last theorem of the day, but I want to point out this is kind of a really useful theorem. Suppose, and let me make clear, your book calls these triangular matrices. I've got to make clear what that means. We say A is one upper triangle if all entries below diagonal are 0. And 2 lower triangle if all entries above diagonal are 0. Yes.
How much faster is the expand than the first?
How much faster is what?
The expand of the columns in the row.
As opposed to just getting on your bulldozer and go. In this particular example, a lot. If I fill that up with 1, 2, 3, 4, 5, 6, 7, 8, counted up to 16 in there, maybe not a lot, right? But if there's lots of zeros in there and shortcuts like that, you can take it's a significant. This seems like a lot, maybe because I'm writing down all the details and saying what the cofactors are or whatever. But when you get used to it, you can go through this actually pretty fast. It's got a lot of zeros in it. And actually, like I said, we're going to come to some theorems that greatly slow this down. But for example, an upper triangular matrix this is upper triangle. The diagonal always goes from upper left to lower right. I don't think this book really makes that completely clear. Maybe it does. upper triangular, lower triangle. If the diagonal goes the other way, it's something different. Although somewhere. There. Yeah. And. It's upper triangular. Well, it's triangle, upper or lower. And we'll say it's an by n matrix. Then. What do you hope to determine that this thing is? One would hope, but it can't be because the identity is. So what's the second easiest? You guys keep trumping me, yeah, but how about in a universe where we could actually do something with this, right? So it's always been one. Product of diagonals. Given the computations we've done, this is probably a huge relief. Because if I give you this matrix, 1, 4, 8, 12, 16, 0, 2, 3, 4, 17, 0, 0, minus 2, 8, 3, 0, 0, 0, 1, 17, 0, 0, 0, 0, 3. The determinant is 1 times 2 times -2 times 1 is 3 is -12.
So can you just row reduce any matrix and then find the determinant that way?
Great question. So why can't you row reduce? You can, sort of, almost. What you need is for row reduction to not change the determinant. Row reduction actually can change the determinant, but in a controllable way. And we'll talk about how to row reduce and give an easier way to do it. But you need to know how to compute it this way. Question. All right, y'all have a fabulous weekend. We'll see you on Monday.
I would just. You know.